All right. So let's work through these last several examples, and I'm going to actually add on to reaction 1 and reaction 3. I'm going to add an extra step so we can discuss directing effects. So with the first problem, it just says predict the products. Doesn't ask for mechanism. Doesn't ask you to put the arrows in. So this particular reaction is going to fall under the classification of a Friedel-Crafts acylation. If you remember when we first started talking about this functional group right here, the carbonyl functional group, well, the acid chloride is the start material, but that particular functional group, when I react that under Friedel-Crafts conditions with aluminum trichloride, right? We've seen this before. It's actually going to add this piece of the functional group to the ring, right? And there's nothing on the ring to dictate where it should go. So my product ends up looking like this. All right. And then with that being the product, now if I added, let's say I wanted to halogenate this, and I did it with a Br2 and iron bromide, iron tribromide. With this functional group, is this a donor or is it an acceptor? Right. Remember, we talked about that. You have donors, and then you have acceptors or electron withdrawing groups. What is a carbonyl? What would that be considered? Would it be considered an acceptor or a donor?
Is it the, because I think you said the benzene will be the nucleophile?
Mm-hmm. It is.
So the carbonyl, it will be the donor.
Well, so when
Electrophile.
we say donor, we're talking about electrons. When we say electron, well, acceptor or electron withdrawing group, right? That is also able to accept electrons. So donors donate electrons. And acceptors accept electrons. When you accept a pair of electrons, what's required to accept electrons? Let me simplify that. Do you need to be positive or negative to accept electrons?
You need a negative charge.
Electrons are negative.
Oh, sorry.
Yeah. So you want to be confused. That's okay. That's okay. But you want to be positive, right? So the carbonyl itself, there's a dipole going towards oxygen. So that carbon in that carbonyl is partially positive. Oxygen is partially negative. So with that being said, the carbonyl is actually an acceptor. Right?
Where would the electrons be accepted? Because oxygen looks like it's pretty full.
Yeah, well, oxygen has a full octet. So does carbon, but carbon is partially positive because of that dipole between itself and oxygen. That's why I have the dipole arrow. Let me redraw it.
Okay.
So the electrons are moving towards oxygen. So that makes carbon more electropositive and able to accept electrons. And if I drew a resonance form, which I can do, here. Right, so it's the carbon that will accept the electrons. right? So with that being said, if I want to add something to the ring, another electrophile to the ring, if this is an acceptor, that means it's going to be a meta directed. Let me go back up to here. So if you have an acceptor on the ring, in this case, it's this example right here, right? The meta position is going to be basically the relationship is a 1-3. So this is 1, that's 2, and that's 3. And then ortho para is going to be 1-2 or 1-4. Don't confuse that with the addition to conjugated diene. Is not the same. It's just the positioning of the substituents, right? So this is anytime you have a acceptor on the ring that can pull electrons out of the ring, either by resonance or by induction, then it's going to cause that the meta position to be activated. So if we go back to here, where's the meta position relative to where that carbonyl is? Right, if this is 1, that's 2, and that's 3. So the fact that the ring is now substituted already, anything I do to it, the carbonyl is going to dictate the product. So with this set of reagents, bromine and then iron 3 bromide, what am I doing? What do those reagents accomplish?
Stability.
Now let's go back to the list of reactions, right? That's a specific set of reactants that accomplish a specific outcome. So anytime you add a halogen.
Oh, is this the phetals?
No, this is not Friedel-Crafts. Friedel-Crafts, so that would be these reactions right here.
Halogenation.
So it's a halogenation. So I want to add a halogen to the ring. So let's go back. Right. The thing is, with the ring is when the ring is already substituted, the halogen has to go where the substituent tells it. So that's why I'm making so much hay about whether or not the carbonyl is a donor or an acceptor, because that's going to dictate where the bromine goes in this next reaction. Right. So the fact that the carbonyl is an acceptor, that means that the bromine can only go meta. It cannot go anywhere else. So the bromine has to go here. Right? And meta, again, in terms of numbering, that's the relationship between the two substituents is 1-3. So it's a 1-3 relationship. All right, questions about that?
Yeah.
Go ahead.
You got, I think I might be confused, but you have BR2 and the iron bromide. But what about the aluminum? What happened to that?
No, that's a different catalyst for a different reaction.
Oh, so okay. So is this second part right here just if this reaction went under something else?
Yes, if I completed the first reaction to get you here.
Okay.
And then I'm treating that with another set of reagents to highlight the directing effects. of the substituents. So if you have an acceptor on the ring, it's going to be a meta director. It's going to activate the meta or the 3 position, and it's going to, by the same token, deactivates the 2 and the 4 position. All right, I'll put that over here.
And you said let me go back, the ortho, the numbers for the ortho para are the 1 and 3?
1, 4.
1, 4.
Mm-hmm.
And this one is 1, 2?
No, meta is 1, 3.
Okay.
So ortho is 1, 2. Para is 1, 4. Those 2 happen together. And
okay.
if there's a donor on the ring, and then meta is 1, 3.
Okay.
So if you have a ring that's already substituted with a substituent like this, that's understood to be 1, this is 2, and that's 3. So this is the position that gets activated if X is an acceptor. If X is an electron withdrawing group, then it's the 3 position where your reactant, your other substituent is going to go. All right, let's do number 2. What will we get from that? This is bromine and the presence of iron bromide. What would the product be from that? You know the ring is going to get substituted, but what's going to end up on the ring?
Br.
Bromine, right? So I can put that anywhere. So bromine and your halogens, we typically think of them as acceptors because they're electronegative atoms. They can cause a dipole, polarized bond. But when the halogen is on an aromatic ring, it's actually a donor. In the aromatic system, it's a donor. All right, so what have I added? Let's see what I want to add. I'll add this. I'm going to do a Friedel-Crafts alkylation. Where's that group going? If there's a donor on the ring, bromine is a donor for aromatics. Where is the alkylation going to take place? Let's answer that first, then we can draw the products.
The 3rd carbon.
So if it's the 3rd carbon, let's number them. 1, 2, 3, and 4. If there's a donor on the ring, the 3rd carbon actually is not going to be activated. Let me show you why. I think I showed it in Wednesday. Let's see. Here. So this is an example of having a donor on the ring right here. And if that's the case, that donor can push electrons into the ring through resonance. So you can see right here, the first resonance form actually has the 2 position activated. Putting 2 in quotes because we normally call it ortho.
Yeah, so are you counting from where the position from where the bromine was?
Yes. So if it can put electrons into the ring, then it's going to activate the 2 position. And then if I draw the next resonance form, it's going to also activate the 4 position. And when I say activate, what I mean is that you put some electrons there because remember, this is electrophilic aromatic substitution. So your ring is acting as a nucleophile, adding, and it's attacking an electrophile. So here, the 4 position is activated. So bromine fits into the, it's in the same class. It's a donor. Just like oxygen, just like a methyl group, if it was attached to the ring, it would be a donor. So if we go back to the example we were looking at, let's see if we can figure this out. So if I have a bromine, which is a donor, right? So this is 2. If we put electrons into the ring like so, let me rearrange those double bonds. That's going to put a pair of electrons on carbon 2. Right, so that's one spot. And then, if we have electrons on carbon 2, then we'll also have a pair of electrons on carbon 4 if we draw the subsequent resonance form. Right, if I did that, then that's also going to put electrons at 4. Right, so those are the spots that get activated and can add an electrophile, 2 and 4. So over here is going to be these two spaces where the electrophile adds. The question is, what am I adding? Right, this is my electrophile. Then it's just the alkyl group that I'm adding. That's why it's called a Friedel-Crafts alkylation. So I'm adding that alkyl group. So my final product is going to look like this. So I have a bromine here, alkyl group here, and then plus this product. Right, so this is my ortho product, and this is the para product. And I also mentioned something about which one is favorite. What do you think? Based on sterics, which one would be favorite? Let's say, let me give you an idea of size of bromine. So bromine is like huge, right? And the bond will be much longer too, but it's a pretty big atom, atomic radius wise. Which one do you think is going to be?
You see which one will be more favorable?
Mm-hmm.
I think maybe the para.
Para is always favored.
I agree with that.
Mm-hmm. Right, so due to sterics, the para is favored. And again, sterics just simply, the way I simplify that, it's just like the atoms have a possibility to touch, and that's not good. Right? If they're close enough that they can bump into each other, that's going to raise the energy of that product, and it's going to make it less favorable. Still, you'll still get some, but the major product is going to be the para. All right. Ran up. It's all right. We can do number 3 down here. Just realized I did the mechanism for this Wednesday. All right. What kind of reaction are we doing here? That iron can be aluminum. Actually, let's make it aluminum. right? What's the product of that reaction?
The
Is this acculation? Not
Yeah.
with the L, but with the C?
Not with the C. Acylation will be here, right? This is the giveaway for acylation. It's an acid chloride as your start material.
Okay, okay.
Alkylation is starting with an alkyl halide. That's the difference between those two reactions.
You said for acylation it's an acid chloride?
Yeah, that's the functional group. Looks like this. Right, so this part is the acid chloride. All right, so here, what's the product here? This is an example of the Crafts alkylation. Just like what we just did up here. So if I have an alkyl halide, aromatic ring, in the presence of a catalyst, it's the alkyl portion of the alkyl halide that's going to get added to the ring, right? Not the halogen itself. If we go back and think about the mechanism, the halogen actually gets pulled off by the catalyst. That's the first step. Any of these reactions, the first step is to prepare your electrophile. So you're going to complex it with the metal and either pull off the one of the halogens, or pull off the halogen, or make the reactant more amenable to accepting a pair of electrons. Right, so this is I'm gonna put it here. All right, that's the alkyl group that gets added.
So I have a question. Does it matter which carbon we attach it to, or are we just always attaching it to the first one?
It doesn't matter. If the ring is not substituted, all the carbons are equal. So they're all equally susceptible to reacting. That's a good question, though. Yeah, unless it's substituted, then everything is fair game. All right, what if I took this and acylated it? What would I get from that? So I'm starting with this. I made it, and the way this will work in a lab, you'll make that first product, isolate it, either run a column or purify some other type of way, probably distillation, purify it, and then you can use it as a start material for a new reaction. So that's what we're doing here. What will happen with that product as your start material if we did a acylation?
Would it attach to the fourth carbon or the second?
Or both?
So
Go ahead.
I was going to say that chlorine is going to insert itself.
Not the chlorine. If it's an acylation, it's this part.
The group.
Yeah.
But the question is, we have to ask this first: is that alkyl group a donor or an acceptor? That's the first question you got to ask before you can think about what the product is going to look like, because if that ring is substituted, then that's going to dictate the outcome. So is the alkyl group, is that a donor or an acceptor? You think it's electron rich or electron poor?
Electron poor.
Why do you say that?
Because carbons aren't very strong.
Well, actually, those carbon bonds are all sp3 carbons. They're pretty electron rich. So that
but do you have electrons to give?
No, but you okay, you're right. That's a good point. You don't have any physical electrons to move, but there's another way to move electrons, and that's by induction. Resonance is one way, but you can also move electrons through induction, so that the alkyl groups are very dense, right? So the electron density is concentrated in those carbon bonds. And the carbon on the ring right here is sp2. So that means it's a little more electronegative. That's sp2. And then this other carbon down here is sp3. So if there's a little dipole, not a strong dipole, but there's a little dipole going this direction.
So what you're saying is it's a donor.
It's a donor, because you're donating not electrons, but electron density into the ring. So let's write that down somewhere. Great observation that it doesn't have any electrons to give. You're at 100% correct about that, but it can donate electron density. Right now, if we know it's a donor, what positions get activated? We know what we're adding to the ring. That's not the question. The question is what does the donor dictate as far as the product is concerned? What sites get activated?
The second.
Said 2 and 4?
Yeah.
So here and here, right? So let's see what we get. We'll have that's one of them. This would be the ortho product. And then I'm also going to have a para product that looks like this. That's 1, 4. And this is 1, 2. All right, and again, the para is going to be favored because of sterics. Further apart you move those groups, the more stable that that product is relative to the ortho product, where the two groups are right up on it. And that terbutyl group that's a pretty big group as well. Very bulky.
Okay, so if it's a donor, it's always going to have an ortho and
two products. Yep, you got if a donor's on the ring, you always get two products, ortho and para.
Okay.
Do you mind explaining? Because I thought we was doing the calculation, but we're doing acylation. Can you explain how? Huh?
In the second step, yes, it was an acylation, but the first step was an alkyl.
Yes. Okay. So my question is, for the second part, the acylation, the difference between this one and the first example we did, because I think in that one, that group was an acceptor, right?
Yes. After we ran the reaction, the first reaction, yeah. So we had a carbonyl attached to the ring, and then it's an acceptor. So anything you add to it is going to add metal. Here, we did an alkylation first. So now we got a donor on the ring. And anytime there's a donor on the ring, you're going to add ortho and para if you do another reaction.
So was it the acid part that made the other one an acceptor?
Yep, you're right.
Okay.
But over here, the acid is after the fact. It's not first, it's second.
Okay, and is that something that will like work each time? Like if there's an acid after, it will be the, you know what I'm saying? Like, I don't think, it's probably not good to remember like that, but.
Well, it's probably, no, it depends on what's on the ring to start with.
Okay.
That's what determines the products, whether they're ortho or para or meta. I started with a ring that had an alkyl group attached to it. So that's a donor. So if I start with my ring substituted with a donor, when I add anything I add to it's got to add ortho para because of the electronics of that ring. The electronic nature of the ring is it's electron rich. So anything I add in with electrophilic aromatic substitution, anything I add to the ring that has a donor on it, it has to go ortho and para like we showed over here. There's another type of aromatic substitution is nucleophilic. It's the opposite. It's the exact opposite. If you have a donor on the ring, then the meta position gets activated. If you have an acceptor on the ring, ortho and para positions get activated. But that's when the ring is acting as an electrophile, not a nucleophile. In this case, what we're talking about is the ring being a nucleophile. Okay. Did that answer your question?
Yeah.
You didn't sound too sure about that. But okay.
Yeah, it did. I'm okay.
All right. So that's the end of aromatics. We're not going to do anything else with this. I think we covered everything we needed to cover. The only thing I didn't spend a lot of time on was naming. But in the grand scheme, that's something that's not as important as knowing how to push the arrows and knowing how to predict the products. So what I want to do is, let me see. This is a lot of stuff. I need to split these notes up. What I want to do now is kind of shift gears and introduce spectroscopy in the last few minutes, and then we'll probably stop a little early. Let me just start a new document. All right. So the next section is going to deal with characterization. Characterizing. The good thing is you've already seen NMR, right? You've already seen infrared. So that's awesome that we've already seen that in lab. So this will be a review and a little bit more detail with the NMR and the infrared, but the fact that you've already been exposed to it means a lot. So now you're not green, right? You're actually coming in with some experience. Right, so we're going to begin this section. And again, with the exam being on Friday, I'm not certain. If there may be mass spec on the exam, maybe not, and maybe a few questions, because that's the easiest out of all of the techniques to understand. Mass spec is the easiest. So we're going to start with that. And then we're going to talk about infrared, and then we're gonna spend a lot of time on NMR. So then the next test that we take, not the one Friday, but the one after that, is probably going to be strictly NMR. And then the last test we take for the final, we're gonna have a bunch of reactions that we're gonna cover. Like, and if you look in the syllabus, they come out of all different parts of different chapters. So make sure you already prepared for that and go ahead and get your mind prepared for that, because it's not gonna be one single chapter. There are multiple chapters that last section is gonna cover. So yeah, mainly when you make, as a matter of fact, let me just do this. When you make something, let me see if I can pull up a paper with the supporting information. When you make a compound in organic chemistry, you have to prove that you made it, right? So there's a lot of different ways to prove it. In the times before spectroscopic techniques were developed, it might be melting points, like you take the melting point and it matches what's known about that compound. Thin layer chromatography, the TLC would match what's known about the compound. Optical rotation was another way of characterizing, but as the technology advanced, better ways for confirming the identity of compounds were developed. So let me see. I'll just pull up the ACS website. And I'll show you what, let's see what I mean. Like anytime you make an organic compound or any compound, you got to prove it. And that's just the bottom line. You can't like just say I made something and not have the proof. That's why it's so, like, we live in such a weird time now where people just like discount evidence. Evidence matters. If you ain't got the evidence, man, don't come to me. Because I'm thinking immediately as a scientist, like I need to see the proof. Let's see. There we go. Let's just do JOC. So when you are studying organic, you're an organic researcher, anything, come on, man. I was talking about some cookies. Jeez. Anything you make, again, you have to prove it. So all this journal, the Journal of Organic Chemistry, is a journal where, research groups submit their work and they submit, hey, we made this and we did it. This is the method. A lot of times new methods are developed and then published. Sometimes it's an improvement on an existing method. Sometimes it's a brand new method. But at any rate, anything that you make, you have to prove that you made it. And so what happens when you submit a publication like this, let me just pick this one. When you submit a paper like this, right, and this is your transformation that you've been working on in your lab, you and your grad students, when that's the case, you say you made these amino acetals and you got 23 examples and the yield is up to 86%. All right, great, prove it. So now you have to submit what's called supporting information. And then supporting information, that's where your spectroscopic data is, right? And I know before COVID, when we did aspirin, we would take the NMRs and I'd have the students put copies of the NMRs at the end of their lab report. That was on purpose because it's similar to what supporting information is. So if you look right here, this is very detailed, by the way. They'll tell you how to do the reaction, right? What the conditions were, and also the procedure, like how to set it up, how to run it. Like there's no such thing as just submitting it and getting it approved. It's got to be peer reviewed. All your ducks got to be in a row. So all of these are just different procedures for how to do this particular reaction. I'm not going to go into detail, but I want to talk about now here, right? So every compound that you make, you have to include a proton NMR, right? So this is the, you see right here, crude proton NMR spectra for deprotection experiment, blah, blah, blah. So this is what you have to submit this. Normally though, you don't submit the crude, you'll submit the pure. Right, so proton and carbon. So a carbon NMR is a little bit different. Instead of looking at the proton nucleus, you're looking at the carbon nucleus. And then for every compound you make, let me go down. Hopefully they got it. Here. Every compound you make has to be characterized in this way. So you have to tell how you purified it. In this case, they use column chromatography, flat on silica gel. And you have to tell the description. So it says a light yellow oil, right? 88 milligrams, so 67% yield. And every peak in the NMR spectrum has to be identified and defined, right? So right here, it's telling you right here that you have a signal. This is all aromatic stuff, by the way. You have 7.3 to 7.24, and the M is what they call a multiplet. So it's not a singlet, it's not a doublet, it's not a triplet or whatever, it's just a multiplet. And it integrates for 2 protons. So every hydrogen that shows up in the NMR spectrum, you got to define it, right? And give what they call coupling constants, which I'm not going to talk about here because we're going to study a whole section on NMR. But you have to give the coupling constant. So this is proton NMR. This is your carbon NMR down here, right? Identifying all the carbons that are present. And then this is your mass spec, high res mass spec. You have to actually, mass spec tells you about the molecular weight. So the molecular weight of this compound is 330.20, and it has to match, and it has to be high res. So this is calculated, and this is what was found. 330.2066 over here was calculated is 330.2064. All that stuff has to match. If it doesn't match, whoever is reviewing the paper is going to ask a question. Why does this not match? Why is the NMR off? So this is like the nuts and bolts of publishing a paper, right? You can have a great idea, but if you don't have the data to support it, it's not going to get published, right? So what we're going to start talking about over the next couple of days are different ways to characterize, right? Again, NMR, mass spec are the two ways. And then they don't have infrared, but back in the day, you used to have to submit infrared information too, because infrared helps you to identify your functional groups. But this is not here in the supporting information, which is shocking. Anyway, let me just run through the methods, define them, and then we'll pick back up on this on Wednesday, if I can get my iPad to come back up. Questions about that? I think sometimes we miss the fact that when stuff gets published, it actually has to it's pretty rigorous too. It goes through a rigorous review. God forbid if your review goes to somebody, a competitor, which happens, somebody that's working in the same area on the same type of transformation, they'll trash your paper and won't think twice about it. All right, so we're going to study basically 3 different techniques: mass spec, mass spectrometry. This tells us about size and molecular weight, right? That's important. And if you make a compound and it doesn't match what the calculated molecular weight is, then it's possible that you have something different, right? We're going to look at infrared, right? Infrared tells you about what functional groups are present. It's a way to identify functional groups. It doesn't tell you anything about the structure. It just tells you what's present, what functional groups are there. Same with mass spec. Mass spec you can't determine structure from mass spec, but you can determine structure from NMR. And that's short for, who can tell me what NMR is short for? What's that acronym for? When we studied, we did it in lab. And you should have at least had minimal exposure to it. Somebody tell me what that means, what the acronym stands for. It's nuclear magnetic resonance, right? And this tells me about the carbon-hydrogen framework of a molecule. You can actually prove a structure based on NMR. It tells me the carbon-hydrogen framework. So over the next few days, a few lectures, we're going to be talking about mass spec and infrared and NMR. So I'm going to send a mass spec video today. There's no quiz for that video, I don't think, on Blackboard. But if there is, I'll have it. I'll make sure it's open. But then we'll talk about infrared. That's one lecture because it's really not that difficult of a topic. And then we're going to talk about NMR. We'll spend most of our time on NMR. Hopefully, we can take another test before Thanksgiving. Hopefully. All right. Questions? Any questions?
Can I ask you a question after?
Sure. If anybody else is here, if you don't have a question, feel free to log out and